So Young's modulus is when we calculate the final stiffness using the stress and the strain. So we use the stress and we use the strain to calculate the Young's modulus. It's force over area, length over extension. We know that the top is Pascal, the bottom has no unit, so Young's modulus is also measured in Pascal. Now, to calculate, sometimes we can simplify this by cross multiplying and getting force times length over area times extension. And that's also an easy way, specifically if we want to calculate some of these values. Okay, so if we have a graph of stress over strain, okay, we also get a directly proportional graph, and then we have a similar point. Now, a material will only obey Ohm's law, the Young's modulus can only be calculated while the material obeys Hooke's law. Now, Hooke's law is the force over the extension, and it looks something similar. So if we pass by the limit of proportionality, the wire or the spring permanently disforms, and the same thing here. We can see here that stress has force in it and that strain has extension in it. So therefore the graph has a similar shape. And when it changes from the directly proportional line, it means that it does not obey Hooke's law anymore. So if we look at this, if we have stress over strain as my x and y axis, the gradient here is Young's modulus. Now, since we can determine the stiffness and the amount of force that we have to put into a string to stretch it, we can also go and look at how much elastic potential energy is stored inside of it. Now, if we go back to our Hooke's law equation for a graph, we see that force over extension, and we learned that force over extension is the spring constant, and that is the stiffness of the wire or the spring in terms of Hooke's law. So if we have this graph, we knew that the gradient was the spring constant. But what happens if we calculate the area under the graph? In this case, it's going to be a triangle, but the force times the extension, force times distance, is equal to the work done. So the work done in stretching either the spring or the metal is calculated by calculating the area under this graph. And in this case, it's a triangle. So to calculate the work done, which is equal to, remember, work done is equal to energy transferred. Okay. To calculate this energy, we're going to look at the work done, and that is when we calculate the area under the graph, which is half force times the extension. Or if we substitute in, let's say we have the spring constant and we have the extension, but we don't have the force, if we substitute that in there, we're going to get that the work done is equal to, if we substitute the F in there, xk, so it's going to be half xk times x, which is going to give me half x squared times k. So two ways to calculate the work done. If we've got the force and the extension, or if we've got the spring constant and the extension. That finishes the chapter of Young's modulus and the section. If you've got any questions, please let me know. Also, I've added a video that you can watch that shows you experimentally how this is done. Have a nice day. Goodbye.